Okay, so we're looking at the selection sort just from yesterday. Just to do a quick review of that. Um, it looks like I'm recording. At least it's sort of trying to. Um, yeah, there we go. So from yesterday, we kind of quickly went over the selection sort, and it's a really simple one. Um, the way it works is to look for the maximum one out of n items. So it's going to kind of start at the first one. That's the maximum. Then it looks at this one. Between those two, that's the maximum. And then it compares the 8 to the 13. 13 still maximum. And then when it gets to the end and it's got the maximum, it just swaps the two. So a swap is a pretty easy operation for a computer to do. And of course, along the way, it's done a lot of comparisons to see what's greater. So there's quite a few operations going on in this one. And it ends up doing one big loop for each item, but within there, it's got to loop and find, which one's the biggest every time, which kind of shrinks as you get sorted, because once you've swapped this, your list is now one element shorter. So it's n minus one times now that you're kind of looping through and doing those comparisons for. We talked about the algorithm, but basically, yeah, it's doing one big loop through everything, where here it's trying to find the position of the maximum element, starting from 0, like the very first element, position 0, and just kind of, as it finds something bigger, it stores the position, not the number, but just the position of the number. And by the end, you know where the biggest thing is, so you can temporarily store it and then overwrite it with the end element and, yeah, move that one back in and shorten your list. So that's kind of the algorithm. It's fairly simple. We talked about the total number of comparisons, but it's basically an n squared algorithm because it's a loop in a loop. So it's of order n squared. Okay, so the new one for today is the insertion sort. It's going to have a similar idea, but it's going to do more shifting and less comparisons. So how it works is we're kind of jumping in midway here, but so we're kind of doing the opposite here. We're sort of saying, okay, the first part of the list is going to get sorted, and you're going to insert things from the end into their proper position. So, this is kind of jumping in after three, possibly, yeah, I guess 3 operations, because it's already gone through 3 loops to find these 3 and put these in the right order. So if k elements have been sorted at the front of the list, we then start with the one in the unsorted part of the list over here on the right, and we're just going to say, okay, 2, where does it go? Okay, we compare it to 5, 5 moves over because 2 is smaller than that. Then we compare it to a 3. Oh, 3's also got to move over. So luckily we've already moved 5 out of the way, because 2 has to go somewhere. So that's why we're shifting them at the same time until we find one. Okay, it's not greater than, or it is greater than that, not less. So then we stick it in there. And then now the sorted part is 4 elements long rather than 3. So it grows each time. So that's also pretty simple. Like, you probably would have thought of that yourself. And when you think about a hand of cards, if you're playing a card game, you might say, okay, let's look at this one. Where does it go? And stick it in the right place. Everything else moves over. Find the next one, stick it in. Like, just keep inserting. That's why it's called the insertion sort. So the algorithm is pretty simple as well. Like, one big loop, starting at the first element. Well, element 0 is by default sorted. Like, if it's list size 1, it's sorted, right? So you don't really need to start at k as 0. You just start at the one after it's the one you have to insert. Either it stays in the same place or it moves in front of it. So yeah, you just kind of store that element you want to insert, and then you start shifting them to the right. So this is kind of like we kind of already did this in the activity with the array, where we were trying to insert a name, and we were doing that by moving things out of the way, right? Moving them to the right. So this is going to move them to the right, and this here is going to make sure we don't go out of bounds, and this here is going to make sure that the one we're trying to insert is smaller than the one we're looking at in the list. It's going to keep moving to the right, or moving to the left, sorry. It's like to check going within the sorted part to find the right spot, but shifting them out of the way as it goes. So again, not too tricky of an algorithm to understand and to program. And so, it's got less comparisons than the selection sort, but it does do a lot of shifting out of the way. So it's still, going to do the worst case. It's going to be basically the same n squared. It does have advantages, like when it's almost all sorted, like if by chance you get something that's almost all sorted already, then it only has to move a few elements out of place. So that's actually a time where it might perform better than other algorithms, but you just never know if they're in random order, right? So yeah, let me switch gears here and just want to look at from our chapter 13 materials. I made a new link here, and we'll take a look at this. So I like this one a lot. It used to be as a Java app, or applet, sorry, but now they've made it a JavaScript app. So it actually runs kind of like an interactive web page, right? So so I just kind of loaded it and started with whatever sort we want. You see, this one's not in the textbook. It might be interesting to just take a quick look at the first one here, the bubble sort. So you can choose the sort you want here, and then you can step through it step by step, and it'll say what it's doing down here. So I'm going to step into it. So it says, basically bubble sort means like the largest item, like the biggest bubble, air bubble, is going to bubble up to the top through this algorithm. So it's also pretty simple to understand. So first of all, it starts out by comparing two adjacent items. You can see these are already in sorted order, but it still has to compare them because it doesn't know. It doesn't need to swap because they're already in order when it compares them. Then it moves on to the next two. This pair are out of order, so it actually swaps them. The swap, you always make a temporary variable, so you can see how it put one in a temporary variable before moving the other one over top. We can see that again here. So it puts it in temp, moves that one over, and then moves the temp back. That's how you would actually write it in your program as well. Okay, these two don't need swapping. These two do need swapping. Okay, so we'll just hit run here to keep it going. All right, so it's doing its swap. So you can see, if you watch it, you can see this biggest element is actually bubbling to the top. And by the time it gets to the end of this one loop, it will have bubbled the biggest element to the top. And now we have a sorted list where the last element is sorted and the rest of it's still unsorted, as you can see. But at least after this move, now the biggest one has bubbled to the top. Now we can just consider the rest of the list, and then we'll do it again. Bubbling that one to the top, and speed it up a bit here. So it's actually telling you how many comparisons it's doing and how many copies it's made of things into memory. So it's kind of a way to track efficiency. And it's not the fastest algorithm. It's also n squared. It takes a long time, yeah. So we can stop it whenever we want, but it's a very simple one. And there is actually an improvement to it that you can make, whereas in one pass, if it doesn't actually swap any elements, then they must be in order, right? So that actually might happen now. So there's no swap. So it could have stopped. It still kept comparing more and more things. So you can kind of make an improved bubble sort where actually yeah, we'll exit early. I don't know if you guys remember the Algorithms movie that we watched last year in grade 11, but they did have one scene where it was they were interviewing Barack Obama on a late night TV show, and they were saying, throwing him weird questions, and then they asked him, like, what is the most efficient sort or something like this, and the audience is laughing like he's not going to know the answer, and he just kind of says, well, I do know that the bubble sort is not the way to go. So yeah, he clearly knew something about computer programming and knew that that is not the fastest sort. But it is an easy sort, right? Easy to program, easy to think of, and yeah, kind of cool. It's got a good name, bubble sort. Selection sort, that's the one where we watched it. If we hit new sort, we're gonna, I'll just run this one. It looks for the max, right? So we'll watch this in fast mode, right? So it's found the max, it moves that to the end, and it loops again, finds the max, loops again, finds the max, moves it, it swaps the two. Like you can see it's swapped, like when it finds the max, it swaps the last element in your unsorted part of your list with that maximum. So the maximum ends up going as far right as it can. And that seemed to go faster, right? It's at the bottom here, it's logging, how many comparisons it had to make and how many copies it had to make. So bubble sort was worse in terms of making copies, but it made the same number of comparisons. And you can time it in seconds as well if you run the time sort. So let's look at insertion. Insertion is the one that we just did. New sort. Okay, so now we're going to look at, okay, obviously this sublist in green is already sorted because it's only one thing. So now we look to the next item beside it, and we got to figure out, okay, where is that going to go? So we temporarily put it there, and we're like, okay, compared to that, it's actually in front of that, so we shift that out of the way, right? And then once it's shifted, that goes there. Now we got the green highlighted part is our sorted list. This right half is unsorted. So we're going to consider this element, the third element there, and we're going to store that off to the side. We're then going to compare it to that and know it's smaller than that, so it moved that out of the way already. We'll compare it with the next one. It happens to go in front of all those, so there was a, two shifts that had to happen. It's kind of the worst case is where they're in reverse order and it's got to do a lot of shifting, right? So we can finish that by running it. Basically, the left side is growing as you're shifting and putting things in the right place. You're inserting them. So that's why it's called the insertion sort. And yeah, so again, it's similar in efficiency. It's n squared. So it's not vastly different or better than the other ones, but it did seem to make less comparisons here, but more copies, right? Yeah, like good question. So the question is, do slower sorting methods serve any purpose? Great question, because if you have like access to sorting methods built into your programming language, like in the arrays class for Java, that one you could say arrays.sort, and it'll do the fastest sort. One of the more like, I guess, recursive sorts that's gonna work the best, right? But there are situations where maybe you don't have a lot of elements, and these sorts actually might work faster than some of the recursive sorts. Like if you look at the graph of your data, when you do the lab, the benchmarks lab, you'll be able to test those against each other. And if you look for lower numbers, like 16 elements or 10 elements, probably the simpler algorithms are better. They probably outperform the others, but the other ones really take over in a big way when you have like 1 million elements. So I don't want to get into the other ones yet, but you can certainly watch them run. But something like you can run run a sort, like I think we did 20, the default is 20 arrays to sort, random arrays of doubles, and then it tells you how long it takes. So this one took 7.4 seconds. If you look down in the log, we can check it with same numbers, like 10,000 elements, but using selection sort. Is it better? Oh yeah, it seems to be a lot better. And then insertion sort, marginally better. And we can try merge sort just to see. Oh, extremely fast, right? So for 10,000 elements, it's gone really fast. And this one's even faster. And it could be by chance, like, just happen to pick a certain random order, like that worked out well, and maybe the next time it's going to be different. But when you do 20 random arrays, you should be able to get rid of some of that randomness. But we can, check the other, like with more data, and see what happens. Yeah, question.
What causes a sort? Like, if I'm doing the same sort multiple times, I get different results. What causes that? Is that like the computer is doing less power, so it can focus more on sorting?
Yeah, probably like a number of things could affect that. It could be, like if your computer's doing some other operations in the
Like in the
background.
background.
Yeah, like you might be listening to Spotify and maybe have some things loaded up into memory that are, maybe it's doing a virus scan at the same time as it's trying to do your sort, and it's sharing the processor. So that could affect it. That's why we really don't want to look at actual times, but it's tempting to just say, hey, like time is a real thing for me. Like how long does it take, right? But you can see how many comparisons it's doing. Maybe this was a bad choice here to do the bubble sort on 100,000 items, but I guess I might have to cancel this one. So it's taken over a minute already. So certainly, like the other ones, if we compare it to bubble sort, which has taken more than a minute here, and it's how many arrays is this? It hasn't even sorted one. What? Okay, we're gonna have to cancel that. We'll move on to like merge and see. Okay, merge is super fast. So it's not much more. Like we had 10,000, now we have 100,000, and it didn't take much more time at all. But certainly that's why computer scientists can compare algorithms based on order of operations, order of magnitude of these algorithms. Like at worst case, it's going to be n squared relationship because it's a loop in a loop, or it's going to be n log n, which means it's a lot more efficient, like the recursive ones. So they kind of consider like how many operations is your computer having to do. Your particular computer might have a SSD, it might work faster to, write to memory, or in fact, it's really writing to RAM, but so maybe your RAM is faster. So it's going to make that faster than some other computer, but generally, like how many comparisons are you doing and how many copies are you making? Just try one more just to see how bad this one is. Yeah, this is pretty bad too. So for 100,000, I don't know what your numbers are, because you might be able to run yours a bit faster than this is doing it in, but yeah, it's interesting to compare. Clearly, there's a marked difference between the recursive algorithms in this case and the ones that are n squared. So yeah. I'm recording. That's slowing my computer down, but this should be running from a server, right? Like here, probably running from whatever place I got this from, probably some university somewhere, I don't know. So yeah, anyways, so in a minute, insertion sort has sorted one of the 20 arrays. So yeah. Anyways, yeah, so that's that's kind of what I wanted to show today. So we kind of know it's pretty easy to figure out how bubble, selection, and insertion sorts work. They're pretty straightforward. We'll look at the other two tomorrow, but I wanted to show this tool because it is a pretty interesting tool, and you can actually copy this data out and you could graph it if you wanted to, but we're going to do that in the benchmarks lab anyways. So if you haven't done that already, this is the idea. You kind of run it 20 times with 20 different random arrays, so that way it does eliminate, like maybe by chance, your one random number generation has given you almost sorted array, which then this insertion sort would win for sure. Yeah. So yeah, the graphing part for the benchmarks, yeah, basically you would take these and you would try and fit sample sizes. So I'll let you guys figure out how to graph, because that's data management. If you really need help, I can help you, but you want to pick sample sizes that are not that big for the n squared sorts, like insertion and selection. So maybe like 1,000, 10,000, maybe 100,000, depends on how long your computer's like. Don't wait for a minute, but you can then graph like how long, like along the x-axis, you could say the sample size, like going along the x-axis and going up and down, you could have like the time, right? So it kind of, as you add more and more elements to your array, it's going up, right? As kind of like a curve. So maybe have, I don't know, like 5 or so, like different sample sizes or whatever you can get. It'll make, the more you get, obviously the smoother the graph will look. Yeah, and then you can on a separate graph put merge and quick, because they're going to be so different that they would look like a line along the 0 millisecond. They wouldn't really show much if they're on the same graph as the other, the n squareds. Yeah, yeah, it might be that you have a fast computer, and if you do, then run bigger items in your array, like more like bigger n sizes. Or you could also, instead of current system.current time millis, you can do nano time, so you could measure in nanoseconds. That's also possible. But just make sure like not to include the randomizing the elements into the array and filling up the array as part of the algorithm. So don't start the timer until after you've done that, and only stop it once it's done the sort. So yeah. Okay, so yeah, so let me just stop sharing and I can turn off the recording. All right.